no conical singularity. Second thing, if beta is not zero, and it's required that it's greater than -1. So if it's not zero, then this point P is a conical singularity. So it's a conical singularity of order beta. Again, it's always greater than -1. And if you use the angle, so it's of this angle. Of this angle. And next thing I need to define is the regularized Gaussian curvature. So I'll do this by using those local coordinates again. So a function K, which is from the surface to R, defined by the following equality. So K is absolute value of that to the power -2 beta, then e to the power -2 phi, then -4 z bar of phi. Well, this is of course a local definition, so it's in the neighborhood here of that point. But this is the regularized Gaussian curvature. Of the metric M. Okay, so this one, it's not the Gaussian curvature, it's indeed the regularized one. So to get the standard Gaussian curvature, we will also need to have a logarithmic term here. So it's if you define it in the standard way, then you put this as a part of the metric potential here. So we need to add the log of the absolute value of z there. It also appears here. And as a result, it will also produce delta function at z equals 0. So you can interpret this as the Gaussian curvature with all delta functions removed. So you drop all those delta functions at the conical singularities. As a result, you get what we call the regularized Gaussian curvature. Okay, so those are the things I'm using. So example, like first one, if we simply take this sector in the Euclidean plane, so R2, and this angle is pi times beta plus 1. And then you glue those two parts of the boundary, so you end up with a cone. It's a flat or Euclidean cone. So this is the tip of the cone. And the angle here is 2 pi beta plus 1. So this one, by using this language, it can be written like this. So we consider the unit disk, and the metric on this unit disk is given like that. So it's simply this and dz squared. So this is the flat one. And let me give you one more example. So a cone of any constant curvature K. So second one, so let's now consider this this metric. So M is absolute value of z to the power 2 beta, then e to the power 2 phi, and then this. And here, this phi, it's the following function of z. So it's log of 2 beta plus 2 and minus log 1 plus k, and then absolute value of z to the power 2 beta plus 2. So if you take this metric potential and define the metric like this, of course beta is greater than -1 as before, then well, on a sufficiently small disk so that this thing is not singular itself, we can say that this disk endowed with this metric, it's actually another cone of angle 2 pi b plus 1 and of regularized Gaussian curvature k. So here k can be 0, then it's basically the previous example. K can be positive, like spherical cone, or it can be negative, then it's a hyperbolic cone. So those are the preliminaries. Now, well, this can be also written in the local geodesic coordinates centered at the tip of the cone, and then it takes the more familiar form, well, at least maybe for some of you. So we can also write the same metric in this form. So those are the local geodesic polar coordinates centered at the tip of this cone or at the vertex. And so this is positive, theta is in this. And then the function h of r and the curvature takes the familiar form. So it's k to the power -1/2 sine of k 1/2 r. In the spherical case, so k greater than 0, spherical matrix. Then if k equals 0, then h is r. So k equals 0, flat case. And finally, takes this form, so hyperbolic sine of k 1/2 r. If it's the hyperbolic case, so k is negative. Hyperbolic metric. Okay, so this is how it looks like if you write it in the geodesic coordinates. Now for the molecular formula. So I'll be, well, maybe it's good to make some references here. So this is essentially taken from Trajanov from two papers. The first one is in the transactions. It's an old one, so 91. And the other one, it's about the polar coordinates. So this one, it's prescribing curvature on the Riemann surfaces or on complex surfaces with conical singularities. And the other one, it's about the polar coordinates. It's from it's good for a year. So second part, conical formula. So I'll be considering a Riemann surface of any genus And then there will be some arc points or equivalently conical points like a P1, P2, P3, and so on. So M phi, it's a conical metric or metric with conical singularities, and we will be writing it like this. So it's the conformal factor and then multiplied by some metric M naught. So M naught, it's a smooth metric. On M. So this is the conformal factor. And this is a metric with conical singularities like discussed before. Metric with conical singularities. So in addition to the previous assumptions on regularity, I'll be assuming that the regularized Gaussian curvature is a smooth function on M. And as a consequence, this function phi here, it's a smooth function everywhere except for the set of those conical singularities. So say we have n of them like this. So those are the conical singularities. Then locally near a conical singularity, so locally near a conical singularity of order J, we have the following. So we take a local holomorphic parameter centered at this singularity. And in this local holomorphic parameter, the metric can be written in this form. So it's absolute value of Z, then the power is double the order of the conical singularity, and then some metric potential, then that squared. So here, even though we assume that the curvature is in C infinity, the regularity we have here is just a continuous function in U. Well, it's smooth outside of the tip of the cone, but at the tip we have only continuity. So the Laplacian associated with this metric can be locally written like this. So it's this minus b to j minus 2 phi j minus 4 dz dz bar. Okay, and we can write similar equalities for the smooth metric, except this factor won't appear there. So it's just here, say phi j of z is z squared. And let's denote the corresponding Laplacian. So it's the Laplace-Beltrami operator induced by this metric. And locally, we can write it like this. So it's minus 2 phi j minus 4 dz dz bar. Okay, so this is what we have locally, and then globally on M. For the first Laplacian, the one which corresponds to the metric with conical singularities, we take the Friedrichs self-adjoint extension. So globally on the surface, this is the Friedrichs self-adjoint extension, and delta naught, it's simply the self-adjoint extension of the corresponding Laplace-Beltrami operator. Okay, so for conical singularities in general, there are many self-adjoint extensions, so we have to pick one of them. This is the standard choice. Okay, so now for those operators, the spectrum consists of discrete eigenvalues of finite multiplicity, and they are both non-negative. So we can introduce the zeta regularized determinant. In the pretty standard way. So we introduce the zeta function where the zero eigenvalue is excluded from consideration. And then the determinant is introduced like this. So it's e to the power minus zeta prime at 0. Formally, it gives the product of our non-zero eigenvalues. Okay, so if you formally differentiate this and plug it in here, you end up with the product of all eigenvalues except for the zeroth eigenvalue. I won't go into details. So here, the short time here trace asymptotic sine wall, just to show that this makes sense. And this can be done by standard results. So this works outside of the conical singularities, and at the conical singularities, we need to show that the logarithmic term in this short time here trace expansion is 0. So this can be done by the methods of Bruning and Seeley. 87. So now everything is ready to formulate the result. So theorem. Polyakov type formula. So it's a comparison formula for two determinants. On the left-hand side, we have the determinant of the conical metric. So under the log, divided by the area of the surface with respect to that metric. In denominator is the determinant of the induced by the smooth metric, delta 0, so self-adjoint extension, divided by the area of the surface in that metric. So this equals 1 over 12 pi, then the integral over m of the Gaussian curvature of the metric m phi, so of the metric with conical singularities, times phi, and integrated with respect to the area of
so it's not
with respect to this metric.
It's not the regularized one.
Yeah, it is regularized one. It's always so k phi or k naught. It's always the regularized Gaussian curvature. Plus a naught phi the a naught. So k naught is the curvature of the smooth metric. So here it's just the usual Gaussian curvature, no regularization is needed, multiplied by phi, and then the area with respect to the smooth metric. So this term, and then everything related to the conical singularities. So 1 over 6 summation with respect to the conical singularities. So beta j is the order of the jth conical singularity. Then phi j at 0 divided by this, and minus psi j at 0, and minus summation of some terms which describe the inputs into the formula that comes solely from the orders of the conical singularities, like this. So let me first write the definition for this guy, even though it's a lengthy formula. So it's 2 times the derivative of the Barnes zeta function with respect to the first argument related at this point. Minus 2 derivatives of the Riemann zeta function at -1, minus b squared over 6b plus 1 log 2. Minus beta over 12 and plus 1/2 log beta plus 1. And the last thing I want to do here is to write the definition of the Barnes zeta function. So the Barnes zeta function of arguments say A, B, and X. So first is defined by the double series. So AM plus BN plus X to the power minus S. Then it's extended analytically to the point 0, and this is just the derivative of that function with respect to S evaluated at that point. And this is the standard Riemann zeta function, the derivative, and evaluated at -1. Okay, so now what?
What's the psi j? Is psi j in the formula?
It comes from, I erased it. So this is the potential of the smooth metric in the local coordinate. So we have two of them. We have M0, and for M0, when we write it in the local coordinates, it's pure psi j dz squared. And for M5, it's 2 beta j e 2 phi j of z squared. So this is the value of this guy at the tip of the cone, and they are continuous. Well, this one is even smooth. And for the second one, this one is the value of this guy at the tip of the cone, and this one is only continuous. Now, in principle, when you write something like this, the next question is whether it depends on the choice of the local parameter is not, or not. So here, this combination is coordinate independent. So whether you write it in one holomorphic parameter or in another one, if they are both centered at the same point at the tip. So this thing is invariant. So coordinate independent. It's a simple exercise on differentiation. So those terms starting from here, they describe how the determinant in the conical metric depends on those conical singularities, because we compare this determinant to a determinant in the smooth metric. Which is a new formula. Some remarks are in order. So first of all, the function, this one, it's a real analytic function of the orders. So if you consider the interval from -1 to infinity and consider this function on this interval, it's real analytic. Second thing, if we just include a regular point as a marked point, so as a conical point of order 0, then naturally you expect that all those guys, they disappear. Well, this one clearly disappears. If beta is 0, this guy disappears. So in fact, this at 0 is also 0. It's easy to verify this. Next, so number 3, if we consider this, then actually this guy goes to infinity as beta goes to -1 from the right, or as beta goes to infinity, so it's unbound. Next thing, well, it's positive infinity here, and negative infinity as beta goes to positive infinity. This is what we have. And then even though there is a cumbersome definition for this function, it can be easily evaluated for conical singularities of rational orders. If it's a rational order, this thing can be always written in terms of the derivative of Riemann zeta and some linear combination of the standard gamma functions. I won't write this. I'll just illustrate this by letting you know that if it's a conical singularity of order -1/2, so the angle is pi. The angle is pi, then it's simply this minus this plus 1/24. So angle pi. Angle pi. Okay, so actually this is a theorem from my paper in Journal of Functional Analysis, which is here, and at Archive it was posted in 2019.
Sorry,
disclaimer, yeah.
So the C beta go to plus infinity when we approach -1, but what about the whole expression? Can we say?
It's not obvious at all. It depends on the metrics. So I don't know.
So then do you think it's possible that if we choose these phi j's in a particular way, then
I'll show you examples if time permits.
Okay.
So disclaimer, this formula was actually proved under an additional assumption on the regularity of this metric. But I think it can be relaxed, so I won't go into details here just to save time. So it's real analyticity of this metric under the dilation near a tip of a cone. Like you stretch the metric with respect to the scaling, the potential is supposed to be analytic, but this is just a technical assumption. So I won't go into details here. I only mentioned that for any constant curvature metric, this assumption is a priori satisfied. So if we consider anything which is of constant regularized constant curvature, then this is all satisfied. Okay, so examples. Well, first example, if there are no conical singularities, or equivalently, all the orders, they are zeros for any j. Then as discussed, this guy disappears, and this one is just the formula due to Polyakov written in a bit different form. So then the integral with respect to the area was the other integral. So it's actually probably the same thing as in the classical formula of Polyakov. So it's this integrated with respect to this area and plus the integral k naught by a naught. So if the potential phi is a smooth function, it's just like Stokes' formula to write this in that form. So it's exactly the same thing. So it's Polyakov formula for this year, and for the mathematical it's also the starting point in the paper of Osgood, Phillips, and Sarnak in functional analysis in '88. So second remark. Now let's consider a sphere with a flat metric. So the surface is just the Riemann sphere and has the singular metric and phi. Let's take a flat metric. So summation with respect to j, then z minus j. So z sub j is just the coordinate of a conical singularity, and they are of orders beta j. So this one. Well, after rescaling, any flat metric on the sphere can be written like this. So in general, you will also have a rescaling coefficient here, but otherwise it's the general one. It's because of Troyanov's theorem, 86. So now we have an explicit form for the metric with conical singularities, which means we can extract from here the information about this guy, curvature, and everything else. Then what we get as a result, just by substituting this into the formula, and as the smooth metric, I just take the standard metric on the round sphere, and the determinant for it is known. So this thing is known, this thing is known, just the standard round sphere of area for pi. This thing is simply 1 and so on. So substitute, integrate, and this is what we get. So it's log that delta phi over the area of the Riemann sphere with respect to this metric. So this is 1/6 summation with respect to j, summation with respect to I, such that I is not j. Then beta I, beta j divided by beta j plus 1. And log of the distance, equivalent distance between the conical singularities, and minus the sum with respect to j of those functions c at beta j. Then there is also something which doesn't depend anything, just a constant. So this guy plus 1/6 and minus log pi. This is a simple consequence of that formula, just an example. But at the same time, it's equivalent to the famous Korel-Solomonson formula. It's on archive, like they have two papers. The first one was published. This one is available on archive only, but it's a famous result. It's a partially heuristic formula for determinants sphere with respect to this metric. And actually what we obtained is the very first mathematical proof of this formula. It's one of the examples. Next one, now, like I wrote the formula for comparing determinants of a metric with conical singularities to a smooth metric. Well, of course, it can be generalized to the case of two singular metrics. You can always smooth conical metric, and the resulting smooth metric is in the same conformal class. And it allows you to compare determinant of a conical metric to a determinant of a conical metric. Like what you do, you compare a conical metric to a smooth conical metric, then that smooth one to another conical metric. As a result, you get a comparison formula for two conical metrics. So next remark, two metrics with conical singularities. Then the formula takes the following form. Maybe I just correct this one. So from now on, those are two conical metrics, which means this is now a regularized Gaussian curvature, not the smooth one. And then actually what we have are two other terms like before. Now it's not only this one, but also the corresponding term for the second conical metric. So it's alpha j, then this term minus this term, and minus summation with respect to j of c at beta j minus c minus c at alpha j. Okay, so now those are two metrics with conical singularities, and they are both locally written like this, or m-phi as before. It's this one, z squared, and m0. Now it also has this factor, the singular one. Z squared. So now there are two metrics with conical singularities. If one of them has a conical singularity at the point pi j and the order of the other one is 0, just one of them has conical singularity at pi j, then one of the terms disappears and no problem at all. So this is what we have. And if we consider a particular case of two singular metrics with zero Gaussian curvature, so two flat metrics, k phi equals k naught, and they're both zeros. And in addition, if we have this like for any j, either this one is 0 or that one is 0. So either one, the first metric has a conical singularity at this point, or the second one, but not simultaneously. Then is the situation studied before by Kokotov in 2013, sorry. In 2013. In contrast to this result, this term, the corresponding term, it was written in invariant form. So here, the strong side is that this is coordinate independent and this one is coordinate independent. In his paper, he was writing those metrics in very special local coordinates. For a flat metric, it's just the special coordinate in which it takes this form. No one knows if you can write those two metrics so that this term disappears and this term disappears simultaneously. So that's the difficulty, and that's why there is this restriction there, but not here, so it's removed. In addition, this guy was not written explicitly, so now we know it's in explicit form. Okay, so next one, case B. If for any j, we have this, so beta j equals alpha j, then this formula, it reduces to the Polyakov type formula by Aldana, Kirsten, and Rowlett. Reprint, so R5, 2020. So this one, it's a consequence of this one. You only need to assume that this is the same as this. Well, I should also say that there is a version of this formula for surface with smooth boundary, but the conical points are not allowed to be on the boundary. So the corresponding boundary terms here, they are essentially the same as in the smooth version of the formula, which is due to Alvarez, and it's called Alvarez-Polyakov formula. It's just a kind of regularization, Stokes theorem. Because if you write it in the form, the classical one with gradient for conical metrics, it's divergent. So some regularization, but not very different from this one. So I skip this, and now let's consider some extremal properties of determinants. So as I mentioned already, the corresponding smooth version of this formula, it was the starting point in the series of the classical series of papers by Osgood, Phillips, and Sarnak. So let's see what changes in this situation if we consider conical metrics. So let's just consider the simplest case, the case of Riemann sphere. Riemann sphere, so Riemann sphere C of fixed area. Let's denote that area by capital A, constant curvature. Constant curvature and with pure conical singularities only. Conical singularities. Then, because of result due to Trayanov, the orders of those two conical singularities, they are equal. So let's denote them by beta. And the regularized Gaussian curvature, it's positive. So in fact, up to some isometry, the metric on the Riemann sphere can be written like this. So it's an explicit formula. One here Z beta plus 1 squared plus 8 phi here beta plus 2 and everything squared. So m phi is now in the explicit form. I can compare this metric to the standard round metric again. I just substitute everything into the formula and do some integration. As a result, I get the explicit formula for the determinant of Laplacian in this metric. This metric is singular, so there are two conical singularities. The first one is at 0, so the corresponding divisor, it's beta 0 plus beta infinity. The first one is placed at 0, the other one is placed at infinity. I won't be writing the corresponding explicit formula for the determinant. I'll just discuss the consequences, like the resulting extremal properties. So theorem. So it's also from my paper in the Journal of Functional Analysis. So first, there are two situations here. So mu, it's kind of parameter responsible for the location of the conical singularities. So it affects the geodesic distance between those two conical singularities. And beta is just the order of the singularities. There are two cases here. So either the parameter mu is 0, and it means those two singularities, they are antipodal, and the picture is like American football or spindle. Like the resulting Riemann sphere with that metric is isometric to the standard spindle. So it's one conical singularity of order beta here, and the other one of order beta here, rotational symmetry. Or mu is not 0. Then beta can be only a natural number and nothing else. And then the corresponding Riemann sphere with that metric can be visualized like this. So you take the standard round sphere with a cut from one point to another one. And you take a copy of it with the same cut. Then you identify this side, but you come from here with this side, and this one with that one. So as a result, the cone angle is 2 pi here plus 2 pi there. In total, it's 4 pi. Same applies to this point. And mu, the parameter mu, is responsible for the geodesic distance between those two conical singularities. So as mu goes to infinity, those two conical singularities, they become closer, closer, and closer. In the limit, the surface degenerates, and we obtain two spheres. The general case of this order, not of order 1, of order 2, and so on, can be obtained in the same way. You just take more spheres and glue them in the similar way. So this is the illustration of what's happening there. And so in this case, if we consider the degeneration as those two common points collapse, which means the geodesic distance between them go to 0, then the determinant of Laplacian actually also goes to 0, which is not very surprising. This is somehow what you expect. It remains bounded. However, in the second case, this one, the mu is out of the game, and the only thing you can vary is
sorry, D is you take the distance between the two.
D is the geodesic distance between those two conical points.
Yeah,
and it's degeneration. In the limit, you get two separate spheres. So in this case, there is nothing surprising. It's just the determinant goes to 0. It follows from the explicit formula, like integration. Okay, nothing surprising. Second case, what happens if you vary the angle of the conical singularity? So first result, if we consider this case and we consider the determinant is a function of our beta, then this function is real analytic. This function is real analytic. Second assertion, for any A greater than 0, so A is the total area of the Riemann sphere, and it is fixed. It is fixed. So for any area, we have the following thing. So the determinant, it goes to positive infinity as beta approaches -1 from the right. So in other words, as the angles of those conical singularities go to 0, so the determinant goes to infinity, unbounded. Same thing happens if beta goes to positive infinity. So this is the first part of this assertion. Second part, if we consider the derivative of this function with respect to beta, so determinant of this thing, and evaluate it at beta 0, this is always 0 for any value of A. So the round sphere is the stationary point of the determinant. I'm sorry, if you compare this to the classical situation described by Osgood, Phillips, and Sarnak, they were studying the smooth metrics on the sphere. And then it has absolute maximum on the standard round sphere. Okay, so for now, we know that the determinant, if we allow for conical singularities, it is unbounded from above, so it blows up. Plus the standard round sphere, it's always a stationary point for any value of the area. For any value of the area. Next, maybe now I can read it.
Sorry, in this limit, so it's for the American football?
Yes, it is, because otherwise you can't consider non-integer values of beta.
So at the same time, the area is shrinking, right? When beta goes to...
Area is fixed. Curvature is changing.
Okay.
Area is fixed. It's the same setting as in the Osgood, Phillips, Sarnak. We only allow for conical singularities, and the curvature is constant, the regularized curvature. The regularized curvature is constant. Okay, something a bit more surprising. Statement number 3. If the area A is sufficiently large, so if A is larger than a certain value, if it's larger than a certain value, for example, this is what happens if you consider the area for pi. So if area is for pi, then it's sufficiently large. Then we have the following thing. So the determinant A. So this stationary point, it's a local maximum. Then this stationary point is a local maximum of this function. Of this function. Number 4, if A is smaller than another, possibly another certain value. Then, well, for example, if area is less than 1, then it is sufficiently small. Then the stationary point is the absolute minimum. So this stationary point is the absolute minimum of the same function. Okay, so in particular, if we consider area for pi matrix on the sphere, so this stationary point are local maximum, and that local maximum, it's exactly the absolute maximum in the result of Osgood, Phillips, and Sarnak, which means I introduce conical metrics and try to repeat what Osgood, Phillips, and Sarnak did. In this most case, there is no extremum on the sphere. A simple example. And even more, everything depends on area. If the area is sufficiently large, then what you have, it's a local maximum. If the area is sufficiently small, then this point, it's the minimum. Like take the smooth matrix, maximize the determinant, you come to this point. Then introduce the conical singularities, and like the determinant goes to infinity. Yeah. So maybe this is where I stop because it's about the time.
Thank you. So are there any questions or remarks? So again, going back to the case where beta goes to 0 with this American football, so the metric degenerate as well in the process.
Yes, it does, of course.
It's blowing up then, or it's
so you keep the area constant, and you can write what happens to the curvature by using the Gauss-Bonnet theorem. So area is fixed, and then the curvature becomes a function of the angle or order of the conical singularity. So when you vary the angles, and you can only vary them simultaneously, they are equal. What you do, you keep the area fixed, and by varying the conical singularities, of course, you change the curvature. Change the curvature. It's constant, but it depends on the angle of the conical singularity. And maybe it's also good to mention that actually to obtain this result, you don't need the theorem, my theorem from Journal of Functional Analysis. This can be done by results of Sperafica and Zerbini. They study determinants on the American footballs. So after some changes, they write integral representations for the determinants, not representations in terms of the Barnes zeta function, but it can be shown that this is the same as that up to some type or in their formula. So it's Sperafica and Zerbini, and the correction to that formula, it was noticed by Klevtsov, I think in this year for this Sperafica and Zerbini. I don't remember the year, sorry. So it can be done here, but not there. So for this one, either it's integration, like I said, and actually here beta can also go to infinity, but through the integers only. And it's the same result, so the determinant is unbounded.
What about the situation where you have a smooth family of metric with conical angle, you let the angle goes to 0. And I guess there are examples where it tends to Riemann surface with cusp. So in this case, now
sorry? So you want
you let the angle goes to 0, so beta goes to -1, and then geometrically there are examples where the metric converge to a metric with cusp. What happened in this case? Is the Riemann blowing up, or
it's a topic for another talk. So I have explicit formulas for the constant curvature metrics with 3 conical singularities on the sphere, so they can be positive the curvature can be positive, 0, or negative. And this is like exactly what I studied there, except I don't yet consider the degeneration of cones to cusps. It's something I have in mind, but it's not yet done. But yes, in short, the determinant, of course, it goes to infinity there. For the hyperbolic case, it's not a surprise because otherwise you won't need like relative determinants or any kind of regularization, possibly, right? So it's not very surprising, but yes, as a cone degenerates, the determinant goes up without any bound.
Mm-hmm. So I had a question about the constancy of beta.
Mm-hmm.
Is that just the zeta prime at 0 of the cone?
Excuse me?
It will be just the contribution of a finite completed cone. I mean, it's like, will be, if you take just the cone,
yeah,
and truncate it, and then you compute the determinant there.
So you want to take a flat cone?
Yes. And
vary the angle?
Well, that's similar to what we did, but we just computed the determinant of the cone, and the expression was very similar, but just a little bit different for the determinant of the cone. So I just wanted to ask you, what is, so like, where this term C of beta comes from?
If I understand your question correctly, then you're asking how to compare yours formula to what you obtain by using those formulas.
No, I think I know, but yeah, so I know that comes from the cone, but I would like to know what part.
Okay, so in the first part of my talk, I wrote explicit form of hyperbolic, spherical, and flat metric for any cone and the coniverse. So you take this metric, and you compare this to the smooth flat metric on the disk. You put both of them into a formula like I wrote, but on the disk. So it also has the boundary term, and you compute it. You get the explicit formula for constant curvature cones, and also you get dependence on the angle. So you get explicit formula. It's in agreement with our earlier results by Strafiker. In particular so he only had results for flat cone. Again, it was written in terms of some integral representations, but if you like carefully convert those integral representations into Barnes zeta function, you see that they are in one-to-one correspondence. And actually, his result for the flat cones, it's my starting point in GFA paper. So I use those results. Okay. Well, in addition, you also get determinants for spherical and hyperbolic cones. And there is another way to obtain the same results. You just start with the spindle and plot it by using the FK formula. So the formula is the same. Of course, you need to prove that it's valid for surfaces with conical singularities, but it's a part of what I did in Journal of Functional Analysis. So you cut it here, and after some wise cuts, not at any circle, but if you adjust the circle, well, roughly speaking, then the resulting determinant, it's an analytic function of the curvature. So you get cone for any positive curvature after cutting the spindle. Then by analytic continuation, you get the flat case and the hyperbolic case. It's another way to obtain the same result. I hope I addressed your question.
But but this contribution of the constant C of beta is the same without matter the curvature.
Yeah, this is what I also mentioned. So those terms with C beta, they come solely from the orders of the conical singularities. They are the same for surfaces of any curvature. Even if you consider non-constant curvature surfaces, C beta is still the same. So it has something to do with the pure singularity only, so with the angle or order of conical singularity, not with what's happening around it.
Okay, are there any other questions in the audience, maybe? online. Okay. Nobody shows up. So I think it's time to send the speaker.